and I will hand it over to my group to let me know. You guys can play a little bit. Just make sure you can annotate on the screen. There should be plenty of space for it. But the presentation will be hosted on my computer, and I'll try to help you get through what we're doing.
Did you make me and Siani co-host so we could annotate?
You know what? I think you should be able to annotate at any time. I believe I have you tried and it's saying you can't because you're not a co-host?
Oh, wait, hold on.
Yeah.
I
You know,
think
some people be locking y'all up and making it so you can't do stuff. I don't believe in that. I mean, I know how to find out who is writing on the screen, so I'll just fail you.
Thank you.
All right, I did make you co-host, but like I said, I think you had that ability anyway.
I did.
Yep.
I just didn't know that. Thank you.
All right, so this right now is just going over the questions, right? And then the next slide is kind of where we get into the answers. So I actually will just skip this. Just letting you know that number one was items 1A, 1B, 1C, 1D, 1E. And it was a lot of questions in which you had to answer whether it's true or false. And the kicker with this is that knowing whether the answer is true or false, it's based off previous reading. And not just reading, but kind of like retention and understanding about what we were talking about in the past. All right.
Okay. Hi, guys. Good morning. I will be answering 1A through C for you guys. So let's get started. Okay, so for 1A, when testing a claim with 10 matched pairs of heights, hypothesis tests using the p-value method, critical value method, and confidence interval method will all result in the same conclusion. So the answer for this one is true, and that is because the hypothesis test, I hate saying that word, the hypothesis test, the p-value method, and the critical value method use the same distribution. Oh, is that the answer too? Wait.
I'm trying to help you. I'm telling you, yes, sir.
Well, they use the same distribution and they have the same standard error. Okay. Is that enough explaining, or do I have to go in more?
You know, if you think that's what you got it. You know what I mean? Again, I guess the content is on the screen, you know, to sit back and that kind of help you kind of know the answer already when we were doing the work this weekend. Actually, no, this was last week for you. But again, I would just use everything here. And I think if you can understand it and we don't have any questions, we can move forward. The one thing I did have on here is kind of the page number, again, just to prove to us that we have read this before. This information is on page 444. If you don't believe what Nyrese is saying, you can go look at it. But it talks about how the reason why they are going to have the same result is from this. I mean, there's a specific section in this chapter talking about, are they equivalent methods? And as a result, there's something on the homework. I've always talked about there's a straight line between what you read, what we talk about in class, and what you're tested on. And I do this right now to help you guys see that straight line. It's really there. But again, it's also an issue of making sure you understand that line. And that's why we're kind of doing this activity we're doing right now.
Yes. Amber, do you have any questions about 1A?
No, thank you.
You're welcome, dude. I got you. Okay. 1B. Dr. Barnes, you gotta change it.
Okay, that's what's wrong. There we go.
Thank you. Okay, so 1B. The methods of this section are robust against departures from normality, which means that the distribution of sample differences must be very close to a normal distribution. For this, the answer is false, and that is because, wait, it is false, right? It is false. Yeah, sorry guys, give me 1 second. Yeah, it's false. It's a trick question. So though the section, though they are robust, I don't know what that means, Mr. Barnes. So the normality requirement is loose?
Yes. And you know what? I'll sit back and elaborate this. And honestly, this is beautiful. Please don't feel embarrassed by this, right? This right here, I think helps me. This is what I love as an instructor, getting in and seeing kind of like how the breakdown between what's stated and kind of like applying it, right? Now, the question is are the methods of this section robust against departures from normality, right? Now it goes into detail. This might be viewed as kind of throwing you off, right? Which means that the distribution of sample differences must be very close to a normal distribution, right? Now this, yeah, are robust against departures from the normal distribution, right? The answer is false. And the reason why it is false is because the follow-up information behind it is different. The follow-up information is not stating that, who was calling me? The follow-up information is not saying that the normality requirement is loose, right? Up here, it's asking, which means that the sample differences must be very close. So they must be very close to normal or else we can't use it. These two statements don't match up for those reasons. And that's the reason why it is false. So yeah, this is a trick question. Honestly, every time I teach this course, I get to the point where I feel as if I want to write this textbook on my own, but it's just too much. I can't. This is let me tell you, this is a stats nerd sitting back here thinking that this is clear to everyone. And it really is not. All right, I got something in the chat, so I'm going to add this to our discussion. This is chapter 9.3 that we're currently doing right now. So you're absolutely right, Nyrese. Like the first part of this is almost carbon copy, right? But then after the comma, they're saying exactly the opposite. Our requirement, which is on page 443, is saying the normality requirement is loose, whereas the follow-up right here is saying that no, in order for it to work, it must be very close to a normal distribution. That I tell you, that's a stats nerd trying to sit back there and think that everybody is attending the detail as he did. And actually now I understand why you were kind of tripped up, Nyrese, when you were doing it, because it tripped me up from my assumption. So again, I understand how we can get this wrong. I actually think I might go in for the homework and maybe give people an extra point for those who've done this, just to make sure. But again, those of us who are watching this and learning from this, that extra point won't be needed because you're watching, you're learning, and you won't submit it the wrong way. Any questions, anybody? All right, now, Nyrese, I'm going to take this from you. And the reason why I'm going to take this from you is because, yeah, I don't like it. Honestly, I was doing this with the group with everybody before. I think there is something, I think this is a typo or an error in the textbook. And I'm actually just going to skip right over C. It's not going to be graded for anybody who is supposed to do it. So if anybody's watching this video and they're going to submit in assignment 9.3, which you can do, right, to get credit for it, right? If you hand in your assignment 9.3, don't even bother with 1C because it's either something that I don't quite understand or it's a typo in the text. And I'm having a difficult time getting an answer from that. But everything that I'm looking for says that the answer they tell us in the back of the book is wrong. So we're going to skip that and then we'll go to D and E. Is that still you, Nyrese, or are we switching over?
D and E, I believe are Siani.
Okay. Is Siani talking and she forgot her mic is muted?
Yeah, I'm doing D&E.
Okay, so we're on D now.
The methods of this section can be used with annual incomes of 50 randomly selected attorneys in North Carolina and 50 randomly selected attorneys in South Carolina. And the answer to this is not true. There is no relationship between the two, and since they are not matched pairs, and the requirements are that the sample data is dependent and they have to be matched pairs.
Exactly. What she's saying right now, there's no relationship between this. There's no relationship between this right here. Now, you guys might be distracted by 50, might be distracted by this 50, but the most important thing is you got to realize these are randomly selected. This is also another group of 50 randomly selected. There's no relationship between those things. These are not matched pairs, and that's what this chapter is all about. Right. And again, she even highlighted what came off from the requirements. You go back there and look at it. The requirements are clearly saying that the very first one, in order for you to use this process, is the sample data are dependent matched pairs. And we do not have that. We do not have that.
With 10 matched pairs of heights, the methods of this section require that we use n equal 20. The answer is not true. Since they are matched pairs, they count as one, so n would equal 10.
All right, now I put a little table down there. Is there any way that you could use that table to kind of help people understand, or?
I would count it as one. On the side, I would just count each level of the table as one, yes.
Yep, I'm actually drawing it right now. You said each level, but you're really referring to like the row, but
Yeah.
here is, that's one, right? And then this right here is another row, right? Since they're matched pairs, and that's just one subject. Now, I don't have 10 in this sheet because it doesn't go down that far, but that's the reason why, since you have 10 matched pairs, right? Even though you might have 10 from whatever the first thing you're matching with 10 of the other, it doesn't mean that you have n equals 20. N is still 10, whether these are from the same person or if they're different people. Because this could be sibling 1, sibling 2, which are different people, or it could be the weight and the height of the same person. It doesn't matter. Since we say it's a matched pair, n is still equal to how many matched pairs we have. All right, who's up for number 2?
I don't think we were planning on doing number 2, Dr. Barnes, but I have number 3.
Oh, we weren't planning on. So you know what? Let me ask you this. We need somebody in the class then. How many participants do we still have? I thought I heard the Zoom chime, somebody leave. Amber or Deja, are either of you able to sit back and help us find the value of D bar or S sub D?
I'm pulling it up right now. Give me 1 second. Sorry.
Okay. And I'm here to help. I'm not going to put you 100% under the bus.
Why Amber is pulling that up, Dr. Barnes, can I say something?
Yep, go ahead.
Do you remember Intro to Psychology when you made your own textbooks?
Mm-hmm. Yep.
Those were the golden days. I love books.
You know what? I still have it. It's not in the wiki anymore. It's in D2L. But yeah, it's still working. I actually do. I still get some positive reactions from that. The students like it. The other thing is just like some of the faculty don't. But you know what? We got some haters around here, so I'm not worried about that too much.
I have it pulled up. So what you want me to just tell you the answers, or how is this?
You know what? How we get about calculating D bar from here. So it's like kind of filling in the values of each of these Ds. We got to do the
You subtract.
and then I'm gonna show y'all how to do the standard deviation of the of D.
Okay. The first one is negative 0.8.
All right, negative. I'm gonna say 0.8. Save me some time.
0.5. Negative 0.5.
Negative 0.5.
Negative 0.1.
Okay,
0.1. No, this one is just 0.1.
there we go.
And then negative 0.1.
Yeah. All right, now how do we get D bar from that? We can't be scared. Nobody knows how to get D bar from that?
It's the
I don't
mean
know if I
value
did
of the
this wrong, but I got D2 minus D1, which seems to be wrong.
D2 minus D1. All right. And where do you mean? Like, can you tell me where that D2, D1 is on this screen, or where you think it should be?
I'm pretty sure I added up all those
These
numbers.
values? Okay. And
Get
what'd you
the
get when you added
values.
them up?
I'm not sure. I really think I did this wrong. I
Ooh,
think
I tell you, you might have did it wrong. But if I sit back and look this up, I'm doing it right now. I'm going to add these values up, right? Let's see what we get. All right, I think I get a negative 1.4. That doesn't seem right though. Let me do this in Excel real quick. I thought it was something else. Yeah, I think I might have used my calculator wrong. All right, now in Excel, we can just sit back and press sum. It's going to add all those up. Oh my goodness, y'all know why I'm doubting myself. Okay, so the answer is exactly what I had it. All right, now what did you get when you attempted that? Was that what you got?
I didn't. I got 0.28 from somewhere. Oh.
All right. Now, what might have happened might have been playing around with the negatives. You know, if you might have forgot to put in a negative, and actually, I think my homework answer might have been off. I'm gonna go check that out a little bit. I don't know why I thought it was like negative 22. That might have been the next problem. Okay. Now, so we added these values up, right? So we got the sum. What do we do with that sum? Because we're trying to get D bar. What does D bar mean?
The mean of the sum.
Okay, so what do we do to get the mean after we get that sum?
We have to divide it by n.
Divided by n. Oh, I love that. Now Reese is speaking some, you know, she's speaking alien, because she gave me an answer which is 100% right, but if you don't know what you're talking about, she ain't helped you. What is n?
5.
5.
All right. We divide it by 5. I knew that was wrong. Now, when we divide that by 5, what do we get?
Negative 0.28. 28.
Negative 0.28. Excellent. Right. And this skill is going to be very important later when we're doing this. Anybody lost on that?
No, for some reason I got that same exact value, the 0.28, but I don't know how I got it. So,
You know, if you want to reach out with me, we can put up on the screen and look at your items. We can find out what you did and how you got there.
Okay.
Yeah, because again, that's the kind of thing that makes you kind of lose hope and interest in what we're doing. This right here, one thing I tell people to do when you're doing and you're trying to calculate the standard deviation, which is the next thing that's required here, you can do it the hard way, but I encourage us in class to do the online. And when we use the online calculator, I just use Microsoft Bing. You type in online standard deviation statistics calculator. You plug in those values, which are gone now that we put right here that we added up. And the value that we get at the standard deviation is right here. It's actually already on the screen. You guys might not be able to see it, but it's 0.363, right? We can do the standard deviation from technology. You can't do D-bar or anything like that from technology, but you can do that. That was encouraged. We mentioned it in class. That's how we get number 2. Any questions on that? All right, let me clear this and move on to the very next one. Okay, problem number 3.
Okay, that's me. Okay. Units of measures. If the values listed in exercise 2 are changed so that they are expressed in Celsius degrees instead of Fahrenheit degrees, how are the hypothesized test results affected? Yes, if all values are either variable or converted to a different scale, the value of R does not change.
All right, and to add that, you have to remember, this was talked about when?
Well, I know we talked about it in last week's homework, but I don't know if this is last week's homework we're doing. Very confused.
I'm helping you.
Oh, 10.1. So that was last week. No, that was not last week.
All right. But again, that just goes to show that what we're doing, it takes another phrase. They say math is fundamental. Like it really does build on each other. So what we learned last week is not just something that we can drop down and forget about as we move on in the future. We talked about this in 10.1 when we were talking about the properties of the linear correlational coefficient. Now, you guys might have skipped over that, but in 10.2, they argued that regression and multiple regression are nothing more than complex linear correlational coefficients. So all of these rules right here, all of them still apply, even though we're in talking about like, unit 10.4, we might be in unit 9.3 or aspects of that. It's the same exact thing. All right, let me see. All right, who's up for number 4?
You said not to do 4 either.
Yeah.
Oh, you know what? I am so silly. When I meant 4, you know what I really meant? I meant the A, B, C, D from the one that we talked about before. Okay, we'll skip it. We'll definitely skip it. Okay, let's go to 6. This is where it gets crazy.
Start it out. I'll read it. A popular theory is that presidential candidates have an advantage if they are taller than their main opponents. Listed are heights of presidents along with the heights of their main opponents. Use the sample data with a 0.05 significance level to test the claim that for the population of heights of presidents and their main opponents, the differences have a mean greater than 0 centimeters. The first thing we have to do is find the claim, state the claim.
All right. You know, I think my next slide will help you with that. So let me get there. Exactly. All right. So your
Okay.
first thing we do is find a claim. What should I underline or bring attention to? You can just start reading it. I'll trace what you're talking about.
Okay. The population of heights of presidents and their main opponents, the differences have a mean greater than 0 centimeters.
She read right there. And the key is always right here. The word claim is even right there. I always say the claim is written in English, right? The claim is written in English. So we've identified the claim. Put a little check right there. Now, what are the hypotheses?
If the claim is mu is greater than 0. One right now.
All right, greater than 0. Consistent with that. Greater than 0. Oh, you know,
And
I'm messing up. Hold on. Okay, now I'm back.
and the null hypothesis would be mu is less than or equal to 0. It would be that would be the null because the null always has equality. And
Yeah. And since it has equality, we're going to say that is our null. And that makes this our
alternative.
alternative hypothesis. Now, you didn't do it, but I'm going to do it for sakes of just me helping everyone do this. I always tell you, how do you know these statements are right? In your mind, you want to draw a little normal distribution, right? So we have this talking about the value of 0, which is right dead smack in the middle. This first statement, which we got from the claim, is saying greater than 0, right? Now that means if I'm saying greater than, I'm not really accounting for the value of 0, but I am doing everything over here. All this over here is filled out, right? The way that we figure out the other hypothesis, right, is that we need to make sure we cover up the entire distribution. So we need to own this 0 and then everything less than. And then the little joke I was saying before, there's no data point left behind. This entire distribution. And that's how you know you have 2 statements that cover everything. And then after that, you do exactly what she said. You go in, you find which one has equality, which is right there. And that's going to be your null. There's no way to cheat this step. You got to go through that process. And I actually think that this is very important. I'm going to say VIP. This is a very important plot that you should demonstrate to make sure that you're not missing anything. Okay. What else? What's next?
What if find D would be next?
All right. Now, yeah, you can find D.
Okay. Finding D, you would subtract the one president's height by the other one. So it would be 185 subtracted from 171, and that would be 14. The next one would be -2. No, 2. Okay, the next one. Then 8, 5, and -5.
All right. So then we add all these up, and that will equal,
22.
and we divide that by
6.
and that will equal
3.667.
3.667. All right, and that is our D.
D bar.
Okay. Now, anybody not see that? Because I want to get rid of these numbers off the screen so we can move on to the next slide. I know it's not going to match up perfectly with my next slide. So we actually already did D bar. The one thing we didn't do just yet is calculate the T critical. Right now, just like we did before, standard deviation is going to be calculated by using technology. These are all the values that she gave me. I put them on my online statistics calculator. This is probably, I'm gonna say it's the hardest part of what we did. We put those values in, and the standard deviation that we get from this is 6.89, which is written right there. .89. Now we should write these numbers down. You want to write down D bar, and you also want to write down the standard deviation. These numbers are going to be coming in handy a little bit later. All right, now just so I don't want to skip a spot, now we need to find a T critical, right? And a T critical is available with this chart right here. What was our N? You guys remember what our N was for that example that we're doing before?
N was 6.
All right, N equals 6. So our degrees of freedom is N minus 1.
It'll be 5.
Okay. Now, what was our alpha? Do you guys remember what alpha was?
It was, I think it was 0.05.
Yep, 0.05, right? And based off your hypothesis that you did, right? Remember how we do the little distribution? Is it a one-way or is it a two-way tail?
It's a one tail because we only care about mu being greater than 0.
You are absolutely right. So with the information that we have, we got degrees of freedom right here. We got the one tail right here, and we're on the appropriate column. Our T critical, right? When we sit back and draw a distribution like this, the value that is going to represent the area that we can say is significant or not, that number will be indicated by this right here, 2.015. Everybody, please write that down as well. That's going to be important for us to make sure that we understand where we're going to go next. And we're going to go quickly. So make sure you guys write down T critical equals 2.015. Annotate. Now, I'm going to cheat for this because I'm looking at the time and I want to make sure we get here. So I'm actually going to show you guys the math that we use to solve the problem from my homework, as opposed to having them go over. Homework answer, 9.3. Now this is the math. I think many of us are able to crunch the numbers if we want to, right? I'm going to annotate, draw, and cover this up a little bit. Get rid of all of this, nothing but distractions. Cover this up, nothing but distractions. All right, this right here is our equation. This is the equation that we're looking at. We calculated D bar, y'all remember that. Mu of D, the chapter reminds us that we don't calculate it, we assume it's 0. S of D, we use technology. Now, Reese told us what N is several times. So this is the equation that we need to fill in. Based off the information that we used, we calculated the D bar equal 3.667. I made it 3.66. We found out that the standard deviation was a 6.89, which we just showed you on the previous slide. You plug that number here, and then the square root of the N gives us the square root of 6 down below. Following the steps, if you want to. I like to go simple steps. I take the square root of 6, made that with the value here. My next step is also to just solve the denominator, take little baby steps. Still got, I ain't done nothing up top yet. And I divide those two, and the value that I get is 1.301. Now, what do we have to remember? We have to remember what we said, the T critical. I had you guys write that down. This should match. Now, right here, you can't see the distribution because I just drew it a little bit differently. I drew it on a number line, but essentially, this is my tail end of my distribution like this. Now, what we obtain for our T is not in our critical region. And since it's not in our critical region, we fail to reject. Now, if the value that we obtained right here, if it was in our critical region, like beyond 2.015, somewhere up here or something, then we would have had a very different decision. But we're doing with what we have, not with what we want. We always got to remember that. All right, is anybody lost or confused on that? All right, thank you, thank you. Thank you, Siani. All right, let's go back to the problem. And now I know, here's the issue. I don't want you to rush too much, Narish, right? But let's see if we can get through this. It actually is 11:20 at this very moment. It's all yours.
The confidence interval.
Yes. Mm-hmm.
Okay.
Guys, remember, if you look at 6 is a big problem. The first one was what Siani did. It was talking about how to do a hypothesis test. The second part of it is construct the confidence interval that could be used to test a hypothesis. So that's what we're doing here. We're constructing a confidence interval. Now, the first thing we want to do is we want to solve for E. All right, I am going to go back here to this and show it. Now, in order to solve for E, I'm going to put some notations on this homework. This right here, you might remember this value. This is our T critical, like a T alpha. Now, 2.831. Does anybody know or remember where we got that from? That is the value of 6 over 6.893, I believe. That's essentially the standard deviation of D.
0, 90.
Oh, 90 at the very end?
Yeah.
Over N. Remember we talked before, and I'm doing this for you. I'm sorry, Narice. I just want to make sure we're so close to being finished. I want to finish in a good time, right?
Okay.
We talked about why they're equivalent methods. We talked about the reason why they're equivalent methods because they use the same distribution and they use the same standard error. This standard error right here, the S of D divided by the square root of N, is the same exact error I'm going to show you that we use above in this equation. I'm going to highlight it here as well. That's the same thing we used right here. That's why it's equivalent, because in the end, we're using the same thing to measure it. So let's scroll down and I'll show you that this value of 2.813 right here is essentially the same thing that we used above, right? You calculate this, if any, I'm not going to do it now because I want to get out of here, right? But if you divide 6.890 divided by the square root of 6, you will get this value right here. You will get that value. And that value is 2.813. That's what E is. So you multiply our critical value by that same margin of standard error, and then you get a value of E equal to 5.6. And I'm not going to walk through the end because we definitely were like 3 minutes past the time, right? But the next thing that you do when you get the value of E is you take E and you add it to D bar, and then you also subtract it from D bar. And that will give you the confidence interval. And that's exactly what you'll see right here. E is 5.66. We subtract it from D bar here, and then we add it to D bar there. And that gives us our confidence interval. All right, guys, I'm 4 minutes past the due date. And honestly, especially since I started the class, 10 minutes late. Yeah, I'm definitely going to stop and respect your time. Much apologies. Thank you again, Nyrese and Siani. Everybody else in the classroom, look out, because I'm going to be reaching out for other people to meet with me, to learn about the homework, to champion through the homework just like this in future classes. And it will definitely impact your homework assignment grade. But again, you have to show up, you have to perform in order for that to occur. So please check your emails, and I will see you guys Wednesday.
Thank you, Dr. Barnes.
No, thank you. I apologize for putting y'all out there like that.